Here's a question nobody in the press release business wants you to ask. We've got robots that can weld a car chassis to within 0.02 millimeters. Robots that can run, flip, and sort 200 parcels a minute. But a 5-year-old can pick up a grape, a crumpled piece of paper, and a wet sponge without a single line of code or a 3D vision system. No robot on Earth can do all three of those reliably. I've spent over a decade commissioning robot cells, and that gap between what robots can do and what any child does instinctively is the most important story in manufacturing right now. Let's get into it. When most people think about robots in factories, they picture either the scary Terminator version or the boring assembly line version. Both are wrong. What's actually happening in modern production environments is genuinely extraordinary and genuinely misunderstood. A typical automotive body shop today might have 500 robot arms. A FANUC or ABB arm hits positional repeatability of plus narrow, 0.2 millimeters. That's a third the width of a human hair, repeated thousands of times a shift, 24 hours a day, without coffee breaks or sick days. That's not hype. I've watched it happen on the floor. These machines are extraordinary at what they do. The key phrase, at what they do. Here's where it gets interesting, and where the trade press usually stops asking questions. These robots are phenomenally precise, but precision and dexterity are not the same thing. Not even close. Precision means hitting the same point, the same way, every time. That's what robots are built for. Dexterity means adapting to whatever is in front of you. A part that's slightly different, a surface that's slippery, a grip that needs adjusting mid-motion. That's what your hands do automatically, every waking hour without you noticing. I've watched a €250,000 robot cell grind to a complete halt because a batch of brackets arrived oriented 5 degrees differently than the vision system expected. A line technician walked over, picked the bracket up by hand in 2 seconds, and placed it correctly. The robot took 40 minutes and an engineer to sort out. To understand why this is so hard to solve, you have to go back to basic biology. And I promise this is the only time I'll mention biology, because the engineering implication is what matters. Your fingertips have mechanoreceptors, sensory neurons, at densities exceeding 10 per square millimeter of skin. The human hand has 27 degrees of freedom. It integrates pressure, vibration, texture, temperature, and slip all at once, at speeds faster than conscious thought. When you pick up a glass of water, your grip tightens automatically the instant you detect the glass starting to slip. You don't decide to do that. Your nervous system does it before your brain even registers the event. Now look at a standard industrial gripper. 2 paddles, maybe force sensing at the wrist. Effectively binary, gripping or not gripping. No texture feedback, no slip detection, no adjustment mid-grasp. It's not that we haven't tried to build better sensors. We have. The problem runs much deeper than the hardware. Here's what nobody explains clearly. Touch is fundamentally different from vision or hearing as a sensing problem. With a camera, you get a full frame of information before you ever move. With microphones, same thing. Ambient data, continuously available. Touch is local and invasive. The data only arrives the moment you make contact, which is also the moment you've already started changing the state of the object. You're already gripping it before you know what you're gripping. For a robot, that's an incredibly tight loop to close in real time. And here's the second problem. There's no universal standard for tactile data. Vision AI got good fast, partly because there were billions of labeled images to train on. Touch doesn't have that. Every tactile sensor has different geometry, different materials, different noise characteristics. Data from one sensor doesn't transfer to another. So the machine learning approach that worked for vision doesn't work the same way for touch. Not yet. Let me give you a concrete picture from the kind of environments I've worked in. Electronics assembly is where this hits hardest. For rigid components, think standard chip placement, screw fastening in a fixed fixture, industrial robots are outstanding. Success rates above 95%. But the moment you introduce a flexible cable, an irregular connector, a component that needs to be inserted at force into a socket that has some compliance, the numbers fall off a cliff. Published research puts robot success rates for those force-sensitive, flexible assembly tasks somewhere between 30 and 50% without extensive setup and fixturing. Half the time. In a production environment, that's not viable. Which is exactly why, if you walk into most electronics factories, including the ones making the phones in your pocket, you'll still find rows of humans doing cable routing and connector insertion by hand. Not because automation hasn't tried, because touch hasn't been solved. Now here's where it gets genuinely exciting, because the tide is starting to turn. In May 2025, Amazon unveiled a robot called Vulcan at a press event in Dortmund, Germany. It's the first warehouse robot they've deployed with real tactile and force-sensing capability, not just vision. Vulcan can detect the moment it makes contact with an item, measure the force it's applying in real time, and adjust its grip without dropping or crushing the product. The results are significant. It can handle around 75% of the product types in their fulfillment centers, at speeds comparable to a human picker. It's been deployed in Spokane and Hamburg and has processed over 500,000 orders. That's a real number in a real operation, not a lab demo. Crucially, Vulcan uses Universal Robots' ARMS as its hardware platform, the same UR cobots you'll find on assembly lines across Europe. What Amazon brought to the table was the AI layer and the force-sensing integration on top. Touch plus vision. That combination is what's starting to close the gap. Here's a data point that stopped me when I first saw it. A 2025 manipulation benchmark tested state-of-the-art AI models, the best vision language action systems available, on a simple task: pick up a potato chip without crushing it. These are models trained on massive data sets, running on serious hardware. They failed. Vision alone cannot distinguish a holding grasp from a crushing one at the moment of contact. When researchers added tactile sensing to the system, the success rate on that task improved by 80%. 80. On something a toddler does without thinking. That's not a footnote. That's the entire story of where robotic dexterity research is headed. The breakthrough isn't a better robot arm. It's giving robots the ability to feel what they're touching in real time. There's a cost dimension to this that most automation journalists skip entirely. Dexterous robotic hands are extraordinarily expensive relative to the rest of the system. Morgan Stanley's analysis of Tesla's Optimus Gen 2 humanoid robot puts the hands at roughly 17% of the total bill of materials, around $9,500 per unit out of a total hardware cost approaching $50,000 to $60,000 for a single pair of hands. And that's before you factor in the control systems, the tactile sensors, and the AI compute required to run them. Compare that to a human worker who arrives with 2 fully functional hands, self-calibrating tactile systems, and 20-odd years of fine motor training, all included in the headcount. The economic argument for automating dexterous tasks is much harder than it looks, and anyone telling you otherwise hasn't actually had to justify a CAPEX request to a board. This changes the whole conversation about which jobs automation actually threatens first. The conventional wisdom is that repetitive, low-skilled tasks go first. And that's partially true for well-defined, high-volume, rigid-part environments. But the tasks that are hardest to automate aren't the ones that look complicated. They're the ones that require touch. Cable routing, fabric handling, produce packing, final assembly of mixed components, work that involves irregular shapes, compliance, and real-time adjustment. That's where human hands are still irreplaceable. I've seen automation projects stall for years trying to automate tasks that any new hire could learn in a morning, not because we couldn't build the arm, but because we couldn't give it the sense of touch needed to do the job reliably. Your hands are still the most sophisticated end effector ever built. That's not sentiment. That's engineering. None of this means the problem won't be solved. The trajectory is clear. Tactile sensor research is accelerating fast. New materials, new form factors, sensor densities that are starting to approach biological levels in specific frequency ranges. AI models are being trained on contact-rich manipulation tasks with growing datasets. Amazon's Vulcan proves the commercial case is real. Boston Dynamics, Figure AI, and Sanctuary AI are all racing toward dexterous manipulation as their primary technical milestone. The question isn't whether robots will get hands that can feel. It's when and what changes the moment they do. Because the moment a robot can feel what it's touching with the same fidelity a human can, the last category of manual labor that seemed untouchable starts to look very different. That conversation is coming, and most companies aren't ready for it. So here's what I want you to take away from this. Robots are not failing. They are extraordinary at the tasks they were designed for. But the narrative that AI plus robotics equals universal automation, that every manual task is about to disappear, is being sold by people who haven't spent time on the floor. The real picture is more specific and more interesting. Rigid parts, fixed environments, high volume, already automated or close to it. Flexible parts, irregular shapes, force-sensitive assembly, still a human job, for longer than most forecasts suggest. Touch is the last wall, and until it falls, the 5-year-old still wins. If this is the kind of analysis you're not getting anywhere else, no hype, no theory, just the view from the floor, then this channel is built for you. Every Friday and Sunday, I publish a full deep dive. Real projects, real data, real implications. Subscribe so you don't miss the next one. And if you work in manufacturing, automation, or robotics, I'd genuinely like to know what you're seeing on your floor. Drop it in the comments. The revolution is already running in the dark.